Okay, I started recording. So, okay, the contents. Okay, first I will go through the contents of the course. So we today will discuss about the modes of heat transfer and governing laws. Okay, then the first chapter we will discuss the steady state heat conduction. Okay, so that will include the derivation of energy equation and definition of thermal diffusivity. Okay, and the heat conduction through planar, cylindrical, and spherical walls, both the single walls and composite walls. Okay. Then we will discuss about the critical thickness of insulation and thermal contact resistance. Also, we are going to consider the temperature-dependent thermal conductivity, effect of temperature-dependent thermal conductivity. And then we will move on to the next part, that is the another very important thing in the steady state conduction, that is uniform heat generation. Okay, heat conduction with heat generation. And then we will consider extended surfaces. Okay, so in order to increase the heat transfer, we have to increase the surface area, and for that we use different type of pins. And in this case, we consider different cases, like depending on the surface and the tip condition, we have different boundary conditions to be applied and obtain the solutions. So pins will be considered in the next part. And once this part is over, we will move on to the next mode of heat transfer, that is convection heat transfer. Okay, here we derive the dimensionless numbers, okay, that characterize the convection heat transfer. Then the effect of boundary layer, both thermal and hydrodynamic boundary layer on the heat transfer will be discussed. And I will tell you how to use the empirical correlations to calculate the heat transfer coefficient and then estimate the heat transfer. So this is again a very important chapter, but very easy, because as we are not going to do any kind of big analysis, okay, or the obtaining the correlations by experiments, but just use the existing correlations to calculate the heat transfer. So if you understand the selection of correlation, then it is a very easy. Then we will take up the application of convective heat transfer, very important one, very industrial thing. Okay, in the masters, if you are going for masters in thermal sciences, then you have this subject again in a advanced form. Okay, so this is analysis of heat exchangers. So where we discuss different type of heat exchangers and how to estimate the overall heat transfer coefficient and estimation of performance of heat exchanger in terms of effectiveness of heat exchanger, effectiveness of heat exchanger. So we have two methods for that: LMTD, log mean temperature difference method, and number of transfer units, okay, NTU method. So these methods will be discussed clearly in the heat exchanger chapter. Then the final chapter, okay, radiation heat transfer. Okay, we will learn about the thermal radiation, which is electromagnetic in nature. So then the bodies, different bodies like black body, gray body, these definitions will be given to you. And then we will discuss different laws of radiation heat transfer and then estimate radiation heat exchange between the surfaces. Okay, radiation heat exchange between black surfaces and between gray surfaces. Then, in order to reduce the radiation heat transfer, we use a shield called radiation shield, okay, which is highly reflective sheet of metal. So that will reduce the heat transfer rate, and we will consider that in again the final application. And problems will be radiation problems will be solved using electrical analogy. Okay. So this is the final chapter. Okay, so these many things you have to study in radiation heat transfer, and again, you should cultivate the habit of reading textbooks. Okay, it's not enough. Whatever I say in the class, that is not enough. Actually, if you want to have a thorough knowledge of this subject, okay, so you can read the Sengel book, Eunice A. Sengel book. Okay, the first reference here, heat and mass transfer. So it's very descriptive. It has given many practical examples. Okay, very interesting to read also. So as much as possible, there are many copies in the library. Okay, you can share with your friends also, you borrow, and try to read this book. Okay, at least initial part. I mean, chapter 1 to chapters. You read it. Okay, and you can also refer Hallman. Okay, Tirumaleshwar, Fundamentals of Heat Transfer, Heat and Mass Transfer. Okay, so all these books are available in the library, so you can borrow. And okay, I suggest you as read Sengel. Okay. Okay, you can take down this at least 1, 2 references. Okay, so if that is clear, okay, you know now how much you have to study, and okay, use your time judiciously. So we'll start with the introduction directly to the. Okay, so you already have this some knowledge about this subject. Okay, actually everybody has. Even you don't have to be an engineer to have some intuitive knowledge about heat transfer, because we all experience the thermal energy, isn't it? Okay, so can you share some experience of heat transfer? You have studied this maybe in +2, +1, +2. You're okay before entering into engineering. There may be some introduction to heat transfer there also was there. Other than that, you may, I mean, everybody has this some experience of heat transfer, right? So what? So can you share some of your experience?
When you
What is
touch a
it?
object,
Yeah.
when you touch a hot object, the heat of the
Yeah.
hot object is transferred to the hand, and that is filled.
Yes. Okay. When you touch an object, okay, the response quickly. So that depends on how hot is the subject. Okay, how quickly you respond or you remove your hand. Okay, so and also, you know, will touch a very hot subject object for a longer time, you will burn yourself. Okay, that is very common from our childhood experiences, right? So we all with gone to kitchen and we have touched some hot utensils, all those, okay, life experience we have. Other than that, okay, you also use heat transfer or okay, there's uh, control of heat transfer, you can say, for your comfortable living, right? So what do you do that? I mean, where you use this concept of controlling the transfer for your comfort? Any example you can give?
Thermostat.
Thermostat. Okay, thermostat is used. Okay, that's a control unit of your air conditioner. Okay, yeah. So you're uh, given me the switch which controls the on and off function of the air conditioner. So that's what I wanted you to know, that we switch on the fan or switch on AC to control the living environment or to have a comfortable living environment in our room. It's not only that, we also wear particular clothing depending on the season, isn't it? So nobody wears jacket or the sweater in Manipal now. Anybody? No, right? So the reason, properly, okay? So we already know that in summer, what is the clothing should be used. In winter, what is should be the clothing. And all these things are coming to us intuitively or by experience of our life. You know, we come to know about this. So like this, I can go on talking about the uh, importance of heat transfer in our daily life. Okay, so the first thing is, before learning any subject, any course, we have to ask few questions, right? Why and what actually we are going to study in this course? All those questions, I just put it here. So what is heat transfer and what is the difference actually between heat and temperature? Okay. So misunderstanding will be there many times here. So if I ask directly this question also, many of you may not answer this, right? What is the difference between temperature and heat? So anybody can tell me?
Sir, heat signifies the amount of energy present in an object, whereas temperature signifies the flow of it. It's like pressure, it exists, but it flows when there is a difference.
But you did it exactly opposite. I mean, you answered it. Okay, the temperature actually signifies the amount of energy stored in the object. Okay, whereas heat is the energy in transit. Is it correct? No?
Yes,
You answer the question exactly opposite way. Okay, temperature is actually the amount of it signifies the amount of energy stored in a object, okay, or a substance. Whereas heat is energy in transit. Okay, and then we have, okay, everywhere same temperature. We don't have anything. We cannot estimate that transfer of heat, okay, because there is no heat flow. So only when we have a temperature difference, okay. So when there is a temperature gradient or a difference in temperature, then there is a heat transfer, and that is why we use the this one, heat transfer, and heat is a energy in transit, thermal energy in transit. So I will come to those. I'll answer those questions. Okay, the subsequent slides. What do I know about the heat transfer? That's what, okay, we have the experiences from our childhood, okay, by touching or by observing others, also by listening, okay, we have the some knowledge about heat transfer. Then why to study? Okay, this is very important. So what are the applications of heat transfer and why to study this course? Okay, and it's very difficult to say that I can do the justice to this introduction because it's a vast sub course, so it cannot be introduced very niche 1 hour lecture. Okay, so how it is different from thermodynamics, because you already studied thermodynamics 1 and 2, and then why again heat transfer, right? That distinction has to be made, and you should understand that. So we'll answer one by one questions. What is heat transfer? So it's a science that deals with determination of rates of thermal energy transfer. So simply, now from engineering we are going back to science. Okay. So why we consider a science in engineering? That is again a question to be answered. Okay, we study this heat transfer science because it has so many technological applications. Okay, so fundamentally, heat transfer is a science that deals with determination of rates of thermal energy transfer. Okay, so what are the things that will be covered here? So we study different laws of physics. Okay, so we cannot simply say that we cannot put a physical problem into mathematical form, right? We cannot randomly write some equations. So for that, we need some governing laws or laws of physics. Okay, so we make use of laws of physics, and we can put the uh, physical problem into mathematical form. Okay, then we uh, study different techniques for estimating the heat transfer, calculating the heat transfer. Okay, then we can also bring the technology or design and develop the heating and cooling technology. Okay, it's very important for. I mean, we can name many applications for this one. Okay, cooling. Now you are in front of your laptop or your mobile, maybe, right? And when you can see that it's getting heated, slowly getting heated. So it needs cooling. Okay, it cannot leave the electronic components getting become hotter and hotter. Okay, at one point it will stop working. So that means we need cooling technology. For that, we need cooling technology for the batteries. Okay, all to preservation of food, or for summer we need the air conditioner. So then again, other side, okay, we need the uh, heat, okay, for cooking. We need heat energy for generating power, okay, or sometimes in winter we also need heat energy for space heating. So then that means this one heat transfer is actually a very versatile subject which is involved in all disciplines of engineering. So you cannot say that it's only in mechanical engineering. So heat transfer is actually involved in all disciplines of engineering, but particularly in mechanical engineering because we always we deal with this energy conversion systems. Okay, energy conversion system. That means what do you mean by this one? Energy conversion systems. Anybody? Yes, Srinivas.
Yes, sir.
Yeah. Energy conversion. So we convert, okay, the
Sir, a
energy
car.
stored. Yeah,
A car,
okay,
sir.
you can give example, no problem. Okay, so where we have a energy in the form of chemical energy in the form of fuel, okay, and we burnt in the engine cylinder and heat energy is released, and finally what do we do? There's a conversion of energy from one form to another, okay, and finally we convert into mechanical energy. So this is one application in the transport where energy conversion takes place. You have the power production, electric power production by using fossil fuels, nuclear fuels, solar energy. Okay, so all these energy conversion systems involve the heat transfer. Okay, so if you go to any industry, even not only the power, but even if you go to the chemical industry, okay, or a fertilizer industry or any other refinery, uh, right? So you have the many applications of heat exchangers there. So you will find many heat exchangers there because the process involves, okay, these processes involves heat transfer. Okay, so then what's the difference between temperature and heat? It's already we discussed. The temperature is a measure of amount of energy possessed by the molecules of a substance. Okay, see, so temperature is actually the internal energy. So internal energy possessed by the substance is measured using its temperature, right? Energy possessed by a substance is becomes zero if the temperature is absolute zero Kelvin. Okay, so that means at room temperature, every of substance has some amount of energy. But if the substance is above room temperature, uh, then we can extract that energy from that substance by allowing the energy transfer from the substance to another substance. Okay, so this is how it is. Like we can have the heat transfer when there is a temperature difference. Okay, if there is a temperature difference, or temperature determines the direction of heat transfer. Okay, so again, temperature determines the direction of heat transfer because heat flows always from hot region to the colder region. Okay, so but heat is actually the energy, thermal energy in transit. So heat transfer is nothing but energy in transit due to temperature difference. In a short form, you can say heat transfer is nothing but energy in thermal energy. You can put, okay, thermal energy in transit due to temperature difference. Okay, so then this I also discussed just now. So what do I know about heat transfer? Okay, right? Everybody knows about this concept, like when you touch a object, it's hot or cold. Okay. Now here I have put two images, and if I ask which one you prefer to drink coffee or tea, okay. One side you have um, a metal cup, okay, in a small bowl, and then you have a ceramic cup, right? So which one is better to handle? Or
One on the left.
which one?
So the ceramic.
Ceramic is best. Okay. So you know this because ceramic has a low thermal conductivity. And again, if you have to say the first image, you have a hot cup of tea or coffee, and if you want to move it, okay, in this case, they usually put in a smaller bowl. And what is the reason for that?
Area.
Yeah. No. Why this cup of tea is kept in another bowl there?
So you pour it in that bigger bowl and then drink because it becomes colder faster.
Okay. I was expecting this one. Okay, that is one way you can think. But again, if you want to move it from one place to another place, okay, how do you hold it? Hot cup.
On those the thin portions.
Yeah, very thin portions. Why you hold that very thin portion or the rim? Okay, the rim, and you use minimum number of fingers, right?
Yes, sir.
So minimum maybe 3 fingers you use, and you okay lift the cup of uh, tea. So what is the reason actually?
Not in direct contact.
Yeah, you have to minimize the area of heat transfer. That is what you intuitively, without thinking. I mean, without even doing any analysis, you will do that. Okay, you minimize the area of heat transfer. Okay, so that less amount of heat will flow into your body. Okay, so we can put this practical examples and think. Okay, how actually it is ingrained in our memory that about some issues regarding heat transfer. Okay, so then you select the clothing based on the okay uh, seasons. So winter you wear jackets, sweater, all those things. Summer you prefer cotton clothes. Okay. So then again, there are so many applications of heat transfer. Okay, for your comfort, you use the air conditioner or a fan. Okay, and then in the class I used to ask this question that you're at a park and you have a choice to make to sit on a bench. Okay, you have two choices. One is made of metal and one is made of wood. So which one you prefer? Question is clear, right? So you are at a park and there are two benches. Okay, nobody is there on sitting on that benches. One is of made of uh, like steel, stainless steel. Another is wood. So which one you prefer to sit on?
Wood.
Wood, right? Obviously, you prefer the wood. But it's not
Less
because
heat
it's
conductor.
yeah. So why? Because the thermal conductivity of the metal is higher than the wood. Okay. So obviously, when you sit on a wood, less amount of okay. That depends on again on the season. If it is winter, then definitely you will prefer wood. Okay. So the amount of heat that flows from your body will be reduced because of low thermal conductivity of the wood. So then you have also, if you go to buy utensils for your kitchen, okay, then you will see this type of uh, okay reddish brown this one base. Okay, so you know what is this one, right? So that is a copper base. So utensils will come with copper base. And what is the purpose of this?
Good heat conduction.
Yeah, copper is a better conductor of heat than the steel. Okay, so if we have a copper base, then the more energy transfer takes place through that, and we can minimize the losses. Okay, so that is the reason we have the copper base. So like this, we can put many applications and where we already know some things about heat transfer. Then what is the importance or why we need to study this course? So the question is why to study this heat transfer course. Again, I'll start with this first. This one, energy equal to money. Right? Can you elaborate on that? Anybody? Simple, right? Energy is equal to money. But what is the relevance of that to heat transfer? Anybody can think? Think about it.
So like while designing power systems and all.
Yeah. Okay. Power systems.
So we can like control the heat losses.
Yes. Okay. Anywhere.
So that way, power generation
Doesn't matter only energy or any system. Most of the systems, wherever we use, whatever we use, okay, that will consume the energy. And if you minimize that, or if you reduce the losses, then that ultimately results in saving of money, right? So you check your current bill for the last month, okay, and definitely it's going to increase in the next month because the summer is coming and we are going to use more and more fan or the air conditioner, right? So, but if you studied the heat transfer and you applied that concepts of heat transfer before constructing your house, okay, then you can do much better in terms of saving energy, right? By selecting proper materials for the walls, okay, we can reduce the amount of heat conducted from outside into the room, okay, and that will also help in the winter. Winter also it will help that we don't want the heat energy to be lost to the outside environment. So if you are using room heater or anything, so the energy has to be retained inside the house, inside your room. So exactly by designing the proper wall, okay, wall design, insulating wall design, we can reduce the amount of heat energy transferred into the room, and we can reduce the amount of energy consumed for the air conditioner and all those. Okay. Then again, if you go to your kitchen, if you have selected proper, the utensils, okay, material, good, proper material for your utensils, then there also you can save energy. Okay. So this is day-to-day life savings that can result in saving of money. So that's why I put that first sentence, energy equal to money. And if you know the heat transfer properly and that you apply into your real life, then you can save money. So most of the power generation process involves the heat transfer. Okay. And then also transport, that you have the bike or car or bus, whatever it's, or plane. So everywhere we have this, okay, burning of fuel, then conversion of that heat energy into mechanical energy, then heat transfer for comfortable living, that's what, and selection of clothing, cooking, or enjoying healthy food. So heat transfer is very, very important. Now, finally, this question, how it is different from thermodynamics? Because already we have, you have studied this thermodynamics 1 and 2. Okay, where first I think you studied about different laws of thermodynamics, processes, all those things, and later the applied thermodynamics for different cycles. Okay, so here what you studied is in thermodynamics is how much heat is transferred. Okay, so you have a process, okay, isobaric, isochoric, isentropic, isothermal, all those processes you have studied, okay. And during a process, okay, compression, expansion process, all those, okay, in a auto or diesel cycle, know what is the amount of heat transfer and what is the amount of work done, all those things, quantities will be estimated in a thermodynamics. So what you do finally is you estimate, you give the estimate of efficiency in terms of cycle efficiency. And which is the best or efficient cycle, if I ask you? Which is the efficient cycle? So many cycles you have studied, right? In thermodynamics.
Regeneration.
No, in thermodynamics you have studied Otto cycle, diesel cycle, isn't it?
Otto.
Yeah, which is the best efficient one? No? What happened?
Sir, Carnot.
Yeah. Your question is not clear? How many cycles you have studied?
Sir, Carnot.
Yeah, Carnot is the efficient cycle. What is the reason there? Any?
It's ideal.
Ideal cycle. Okay, ideal in the sense you can elaborate much on that. That every process is there reversible adiabatic. Okay, a reversible process, right? So heat transfer exchange takes place in the reversible adiabatic process. So that is why it is a efficient cycle, but it's a ideal. Okay, so no cycle can give better efficiency than Carnot efficiency. Okay, that is what we estimate in thermodynamics. Then what we do in heat transfer then, right? Heat transfer is gives the details of the mode of heat transfer, right? Whether it is conduction, convection, or radiation. Then rate, we estimate rate, okay, time rate, or if it is per second, how much heat energy is transferred. And we can also estimate the losses, okay, temperature distribution in the body. So heat transfer gives us more details. Okay, thermodynamics, we can only estimate the energy transfer in a process complete. Okay, it's in kilojoules, whereas heat transfer is always given as a rate in watts, joules per second. And again, the main difference here is in thermodynamics. If I estimate the efficiency of a cycle, that's it. Okay, I cannot do much, or I cannot do much to improve the efficiency. Okay, whereas the heat transfer, we study in details where the loss is taking place. Okay, how we can minimize those losses. So then what we can do, we can suggest, or we can design the ways to improve the efficiency of a cycle using heat transfer analysis. However, both subjects are complementary to each other. Okay, so in heat transfer also we use the thermodynamics laws. They lay the foundation and framework for the science of heat transfer. Okay, so the laws zeroth law of thermodynamics, which actually tells the direction of heat transfer. Okay, that equilibrium, thermal equilibrium, will tell us the right. What is the reason that thermal equilibrium will be attained? Okay, when there is a temperature difference, ultimately it will flow from higher temperature to the lower temperature, and there will be thermal equilibrium. So the energy in transit, okay, will be estimated. Then we apply the first law of thermodynamics. So what is that? First law of thermodynamics. Anybody? First law of thermodynamics. Wait, this is, I think these three laws should be, yeah, right, well known to you because you have studied thermodynamics 1 and 2. What it says, first law of thermodynamics. Srinivas.
So,
First law of thermodynamics. I think very easy to remember.
sir, you give energy to a system, it's lost in the form of heat and some work is produced.
No, that is not first law of thermodynamics. Okay, so it's a conservation of energy. Energy cannot be created nor be destroyed. That's all. Okay. So first law says the conservation of energy. It's a conservation of energy principle. So energy can neither be created nor be destroyed. That's all. And the second law that tells the quality of energy. Okay, the heat is the lowest quality, and work is superior than heat. So that is, we have there are two statements, right? Kelvin-Planck statement and Clausius statement. Okay. So anyway, the second law tells you that work is superior energy than heat. Okay. Again, the form of so if you rank the energy in a hierarchical way, then heat will come at the bottom, okay, which is the lowest quality of energy, which can be easily lost to the environment. And most of the times, okay, energy loss is in the form of heat. That means if we have a work, okay, if you do the work and then the sum of the work will be spent on the friction. So friction means again generation of heat, and that will be lost. So the heat is the lowest quality and which is easily lost to the environment. Okay, with this, and the first law, yeah, is we can write for a system that is change in energy of a system is nothing but equal to energy into the system minus energy out plus energy generated in the system. So this we can write in terms of rate also. Rate of energy input change is equal to rate of energy in minus rate of energy out plus rate of energy generation. Okay, so this will be used in the heat transfer. So that's why I put here. Okay, now straight away we will go to the heat transfer and we will discuss these three modes of heat transfer, and then I will stop today. Okay. So there are three modes. Okay, conduction, convection, and radiation. Now you have to understand all these three different mechanisms of heat transfer. Okay. So all the modes require a temperature difference. Okay, for the heat transfer to take place, that means there should be a temperature difference. Okay, if everywhere temperature is same, then there is no heat flow. So the first thing for the heat transfer is a temperature difference or temperature gradient. Then the distinction here is conduction and convection. They require a medium or a substance for the heat transfer. Okay, that is a must thing. They require a medium for heat transfer, but radiation does not require any medium. In vacuum, also radiation heat transfer is possible. Okay, and out of the three modes of heat transfer, the radiation is the fastest one. Radiation heat transfer is the fastest one. So these are facts, right? Maybe some of you may not, if you don't understand or have a question, you have to raise now. Radiation heat transfer is the fastest one. What is the speed of radiation heat transfer?
C.
C is equal to 3 into 10 power 8 meter per second. Okay. What is that C?
Speed of radiation. Light.
Speed of radiation, correct. But we also call speed of light. Okay. Speed of electromagnetic radiation is also speed of light. And in vacuum, it suffers no attenuation. That means there is absolute no loss in energy if the radiation travels in the vacuum. Okay, so we will take up the first mode, conduction heat transfer. So how it is takes place? Conduction heat transfer takes place from energy transfer takes place from more energetic particles to the adjacent less energetic ones as a result of interaction between particles. So conduction is the thermal energy transfer, okay, taking place between the particles of a substance. Now you have to realize that if you are considering a solid, okay, you are considering a fluid, there is two different issues here, right? In solid, what is the issue? The atoms or molecules are bound in lattices. They are not free to move. Okay, they are bound in lattices and they are not free to move. Whereas in fluid, the atoms or molecules are free to move. Okay, so this distinction should be brought to your mind clearly. Now, the conduction energy transfer is more. What is the meaning of more energetic particles? So how the temperature is manifested in the solids? Anybody?
The vibration of particles.
Yeah, it is because it is manifested in vibration of particles. Okay, it will be in the lattice itself. It will be at the position fixed in the lattice, but it will vibrate more and more as it gets the material gets heat hotter and hot. Okay, so that is the random vibrations of the particles, and so this energy transfer takes place from adjacent particles, okay, to the next nearest particle, and this propagation will take place from one particle to the other particles, okay. Whereas in fluids, there is also random motion, okay, of the molecules. So when fluid is heated, since molecules are free to move, and their random motion will increase. Okay, so the particles which are hotter, they are having higher random this velocities. Okay, and they collide with the nearest particles, and the energy transfer will take place Okay, so there are two different phenomena. This one depending on the fluid and solid. So conduction is possible in all substances. That means irrespective of whether it is solid phase or liquid or gas. Okay, so conduction is taking place there. Conduction in fluids is due to collision, diffusion of molecules during the random motion, whereas in solids, due to combined effect of vibration of atoms in the lattice. In addition to that, there is also the energy transport by free electrons. Okay, that will be added. I mean, the combined effect of not only vibration, vibration is the major part, but also the free electrons carry the energy. Okay, so that is the conduction in solids. Okay, so this is clear. We will estimate the conduction heat transfer in the solid wall. For that, we use the law, okay, of physics, which is defined by Fourier's law of heat conduction. So, what is as defined? Fourier is a French scientist. So, he has estimated the heat transfer through a planar wall, and he has formulated the law of conduction. Okay, so rate of heat conduction through the homogeneous planar wall is proportional to temperature difference across the wall and the heat transfer area. These are proportional quantities, but inversely proportional to thickness of the wall. So rate of heat transfer, okay, or rate of heat conduction through a homogeneous planar wall is proportional to temperature difference across the wall. So you can see in the picture that there is a wall of thickness L, and if the left side temperature is T1 and on the right side temperature is T2, okay, so T1 minus T2, okay, T1 is greater than T2 here, so there is a temperature difference. Then it is also proportional to area, but that area cannot be shown in this image, okay, easily. So can you see, tell me which is the area? Area should the heat transfer area, which is perpendicular to the, okay, direction of heat transfer. Okay, Q will take place perpendicular to area A, but inversely proportional to thickness of the wall. Thickness. So you write so we can write Q, and see this plus I am going to put this dot. So anyway, then the later class, later part of this course, I will not put this dot because you should understand that whatever the heat quantity that we are estimating, it's a rate of heat transfer. Always it is a time rate. So we don't need to put everywhere because inconvenience every time. So Q is proportional to the conduction through the is proportional to temperature difference. Okay, temperature difference delta T, and the area, and inversely proportional to the thickness of the wall. Okay, and the proportionality constant here is the thermal conductivity. So Q equal to K A delta T by. Okay. Now, if you look at the delta T, or this, we can write it as dt by dx also. This one. Delta T is the temperature Okay, difference, that is T2 minus T1 divided by L. So it is here. Now look at this quantity, T2 minus T1. Is it positive or negative?
Negative.
Negative.
Okay, negative. So in order, if you substitute this one here, then this quantity will be negative. Okay, but we know that if the temperature is higher here and lower here, then it will flow in this direction, positive x direction. So that means we have to make this quantity positive, so that we use a negative sign there. Okay, so don't simply say that. Okay, the heat transfer, Fourier law of heat transfer, is equal to Q equal to minus Ka dt by dx. You have to explain this negative sign is because the temperature gradient. Okay, so heat transfer takes place in the opposite direction of the gradient. Okay, so gradient means what? What is the meaning of gradient?
Slope.
Hmm?
The slope of that curve.
Slope. Okay, slope can be positive or negative, but gradient is always in the increasing direction. Okay, so the temperature gradient is in this direction here. Gradient of temperature is in this direction, so that is why the heat flows opposite to the gradient. Okay, and we have to use negative sign in order to make this quantity positive. That's all. Again, the one more thing here is the proportionality of this. Okay, relationship Q proportional to delta T into A by L. Okay, so that is depends on the material of the wall. Okay, depends on the material of the wall. So the thermodynamic property that that gives the correct estimate of heat transfer is the thermal conductivity. So these are experimentally found detail. This one. Okay, Fourier, when he did the experiment, what he did is he took different material walls. Okay, of the same thickness. He maintained the same temperature across, and he found that. Okay, so some materials allow more heat transfer, some materials don't allow that much heat transfer. So, and he found that the thermal conductivity is the property of the material that, okay, estimate that gives the estimate of heat transfer through that. Okay, constant of proportionality in the Fourier law is the conduction is the thermal conductivity of the material, and its unit here is the watt per meter Kelvin. Okay, so you can also write estimate that. So since Q is in watts, okay, Q equal to minus Ka T. Delta T by L. So you know, if you want to write for K, you can inverse the relationship QL by A delta T. A delta T. So now you substitute for each. This one is Q in watts, Q dot in watts, L is in meters, area in meter squared, and temperature difference in Kelvin. So, okay, you will get the unit watt per meter Kelvin. So, in other words, we can also use the Fourier law, inverse it, to define the thermal conductivity. Right? Thermal conductivity, K, can be defined as the rate of heat transfer through a wall of unit thickness. Unit thickness means its thickness. If you are taking SI units, then 1 meter thickness. Okay, and area of that wall, you take the area. So cross-section area here, that should be 1 meter square. And the temperature difference should be unit. That means if this side is 100, then other side should be 99. Okay, so 1 degree temperature difference should be maintained, and you have to estimate what is the heat transfer through that. That is exactly equal to the thermal conductivity of the material. So rate of heat transfer through a wall of unit thickness per unit area under unit temperature difference. So high K indicates the material is a good heat conductor, and the relatively that value will indicate whether the material is a conductor or insulator, heat insulator. So then it's a very important for the students who have who studied the course of heat transfer. They should have a somewhat idea, about the values of thermal conductivity of different materials. Okay, so frequently used materials in engineering, and the heat transfer problems. I have listed the thermal conductivity values. So these are rounded off. It's not that exactly you will have this thermal conductivity. It depends on the temperature also. With the temperature, the thermal conductivity of material will also change, right? Obviously, because the conduction is a molecular phenomena. Okay, so it depends on the temperature of the material. So highest value in this 2300 is for diamond. Silver has 430 watt per meter Kelvin. Copper 400. So it's in decreasing order. You can see that most of the metals, they are good conductor. Most of the metals are good conductor of heat. Okay. So steel, which is having a thermal conductivity of 50. Okay. So if you have consider the stainless steel, okay, this is carbon steel, stainless steel. So do you think it is more conducting or less conducting than steel?
Less conducting.
Less conducting. Okay. It will be having thermal conductivity of 15 to 25. Okay. Usually the 16 to 19 range, the stainless steel thermal conductivity. Then the mercury, you can see the other insulating materials or non-conducting materials. Okay, so compared to the metals, these have very low thermal conductivity. Concrete 0.8, glass 0.78, water and air. You compare that. Okay, thermal conductivity of air is very small, and the asbestos, which is usually used, but nowadays it's reduced, the use of asbestos in the insulating material. Okay, so rubber 0.13 watt per meter Kelvin. Okay, this table will give you some understanding of which material conducts better and which not. Okay, so then we will consider other mode, that is convection heat transfer. It's a more complex mode of heat transfer. Okay, for your case, it has been simplified in the, like, we are not going in the details of the fluid flow and all those things. So actually, if you want to estimate the convective heat transfer, then you have to study the fluid flow, the velocity profiles, and then experimentally we have to estimate the rate of heat transfer, and from that we have to come back and obtain the heat transfer coefficient. But the job has been very simple for you because existing correlations will only used. But actual heat transfer analysis, you have to derive the correlations, okay, for the applications you consider. So convection is the mode of thermal energy transfer between a solid surface and an adjacent fluid that is in motion. So if fluid is in motion, then only we say it is convection. Okay, understand clearly? Fluid should be in motion, then only it is convection. If the fluid is stationary or there is no bulk motion, okay, if you are looking at the molecular level, every fluid molecules are not fixed at one particular point. Okay, there is a random motion of molecules in the fluid, but the bulk motion is, it will be cancelled out in the random motion. So it's not a visible as a bulk motion. But for convection heat transfer, the fluid should be in motion. So convection involves combined effect of conduction and bulk energy transport by the flowing fluid. Any doubt here? It's a combined effect of conduction. What does that mean? Even though, yeah.
So static plus dynamic.
Static plus dynamic. Okay. Yeah. Even though the fluid is moving in a particular direction, right? Nobody can prevent the random motions in between. Okay. It's actually going in a particular direction, maybe, but the molecules still have the random interactions. Okay. One molecule will collide with the other, and the energy transfer takes place between the molecules. Okay, the intermolecular interactions will be always there. So it's a combined interaction. Okay, combined interaction between the molecules, intermolecular interactions, and the bulk energy transport. That means where the hot fluid will move to one location to other location. So that is how the energy transfer takes place. So one simple example we can give is between the conduction and convection is that if you are sitting in a class, okay, and so this is a simple example, okay, I bought a packet of chocolates and I can ask to distribute those chocolates among yourself without moving from your seat, okay, from the chair you are sitting, you don't move, but you can distribute the chocolates among yourself, right? So this is conduction, that you don't leave your place, but distribute the chocolates to the entire class. Okay, but other ways like I will give handful of chocolates to few students, and they can move in the class and they can distribute to other students. So which involves the motion of students in the class by carrying these chocolates. So this is, you can say it's a form of convection. Okay, so understand clearly there's a distinction between conduction and convection. So in conduction there is no bulk motion is not involved. Okay, so energy is transferred to adjacent particles, okay, without any bulk motion. In convection, definitely there is a motion of molecules, okay, bulk motion of fluid. Okay, then faster the fluid motion, greater is the convection energy transport or heat transport. Okay. The reason here, again, you should understand faster fluid motion means how it will increase the heat transport. Any other idea? You can think about this one. How the increase in fluid motion will increase the heat transport.
Sir, by increasing the motion, you are setting more molecules in motion, right?
Yes,
So the
that is
chances of collisions are more.
okay. That is one thing. Yeah. Another thing you think about that is the capacity. Okay, capacity of heat transport will increase. Capacity in the sense, okay, if you increase the fluid motion or the velocity of the fluid, that means flow rate of mass flow rate is increased, right? Mass flow rate is increased means the same so the fluid has a capacity to store the energy, right? mcp delta t, what we use as the energy stored in the fluid. So if you are increasing the flow rate, that means the mass of the fluid is increased. So the more mass means more energy can be stored in that the fluid. Okay, so that means it can uh, increase the heat transfer. Okay, in the absence of fluid motion, heat transfer between the solid surface and the adjacent fluid is by only conduction. See, irrespective of, it's not always that there should be convection whenever fluid comes. No. Okay. If the fluid is stationary, if it's not, there is no bulk motion of fluid, then still the heat transfer can take place. Sorry, conduction heat transfer will take place between solid and fluid. This is for this. For this, you can see that when you want to make a cup of tea or a coffee, right? You keep the water on the stove, and initially you can see that there is no motion of fluid, but if you dip the finger in the water, you can see that water is heated. Its temperature may be raised to 50, okay, or even 60, 70. You may not feel that the fluid motion, but later, okay, when it nearing to the boiling temperature, you can see the fluid motion. Okay, and this is because of density change. Okay? Because hotter fluid will become lighter. Okay, the molecules go far from each other, and its density will decrease, and because of that, the low density fluid will move up, and the cold, large density or higher density fluid will come down. So this motion will be set up. So in the absence of fluid motion, that means until the fluid motion is set up, or if you are stirring the liquid or you are pumping the fluid, okay, that is external means. Okay, then there is a fluid motion. But if it is no fluid motion, then the energy transfer between a solid surface and the fluid is only by conduction. Okay, so convection, okay, can be grouped into two types. One is post convection, and there is pre convection. Okay, post convection is nothing but the fluid motion is induced by external means. Okay, so in you take any example, like for example, you want to drink the coffee fast, so you want to, okay, reduce this temperature. So what you do is you take a spoon and stir it, right? Or you try to blow air on the top of the fluid layer. So by this, what you do is you set the fluid into motion. So the, okay, colder fluid and hotter fluid will be mixed, and there will be more heat transfer. So what we do is nothing but this external fluid motion is caused by external means. Okay, so that is why it is called post convection. So heat exchangers, if you look, if you consider the, I don't know whether you have seen a heat exchanger, but probably you might have seen a CPU heat sink, right? In back of your desktop computers, there is a fan and there is a heat sink there. So what is the purpose of putting a fan there, right? We are inducing the fluid motion. Air is pumped, air is pushed through through that heat sink, so that the convection heat transfer will increase. Well, the pre-convection, on the other hand, or there's another name for that. That's natural convection. Okay, don't confuse with that. So pre-convection is nothing but the fluid motion is caused by buoyancy forces. Okay, the force causing the fluid motion is natural. It's not because of any other external means. It's simply because of the density variations under temperature gradients. So, okay, hotter fluid definitely have the less density compared to cold fluid. So because of that, right, depending on the region which is getting heated, that fluid will become lighter and it will rise up, and there is cold fluid will come and replace that place. So there is a circulation of fluid, and that is actually pre-convection. Okay, boiling of water, cooling coffee in a still air, that is without using any stirrer or okay. So automatically there will be some convection currents will be there. Okay, so to estimate the rate of heat transfer by convection, we use the Newton's law of cooling, and you can see here. So it's very simple. So rate of heat transfer is proportional to temperature difference. Here the temperature difference in the sense temperature of the fluid and temperature of surface. Okay, difference is nothing but temperature of the fluid. Here I have written T infinity, which is the fluid temperature, and T surface is the surface temperature. So Q is proportional to temperature difference, T infinity minus Ts or Ts minus T infinity. That depending on whichever is larger. Okay. So T infinity and the surface area. Again, the area which is normal to the heat transfer, this surface area there. Okay. So into area. And the proportionality, constant of proportionality is the known as heat transfer coefficient. Heat, okay, convection heat transfer coefficient H. So Q equal to H A delta T. Okay. So delta T can be T. Okay, here I think I made mistake. So this would be T infinity minus Ts. So what is here? The hot surface, okay, and the cold fluid is flowing over that. So there is a heat transfer from the surface to the fluid. But if there is a hot fluid flowing over a cold surface, then the heat transfer is from the fluid to the surface. Okay. So the equation remains same, HA delta T, but only we have to put that whichever temperature is more, that to be put first. Okay. So this quantity should be taken positive, but direction you have to know. Obviously, we know that hot. Okay, if the fluid is hotter than the surface, then it is from the fluid to the surface. Other case, from the surface to the fluid. Again, there is a. I have shown this profile here. That is also very important. We will go to. We'll discuss that, and that is the fluid motion. Okay. You might have heard about that. Okay, boundary layer in case of fluid mechanics. Okay, that was discussed probably. So usually there is a boundary layer, velocity boundary layer at the surface, and because of that we have the problem to the heat transfer. Okay, because even though we have a large fluid flow, velocity of the fluid at the surface is very small. So this fluid gets more and more heated, whereas this fluid, which is away from the surface, will pass over the surface without getting enough heat energy. So that means we need a proper mixing so that we have more heat transfer. Okay. So Newton's law is a very useful tool for us, but the problem with this law is usually we underestimate that there is a quantity, okay, H, which is very complex than the thermal conductivity. Okay, this quantity is much complex quantity. Thermal conductivity is thermodynamic property of the material. That's all. Okay, it's done. But H is not related to the fluid also, not related to surface also. I mean, not completely. It's partially related to everything. Okay. And till now, we don't have any, mathematical ways or to estimate that. So only empirical correlations. That means you understand. Do you understand what is the meaning of correlation? Empirical correlation.
All experiments, no theory.
Or experiments, no theory. Okay. No, it's like, okay, we derive an equation. We will obtain an equation from the experimental data. Okay. So we use a relation to obtain H value from the experimental data. That means we have to conduct many experiments, and from that experiment we can estimate H value. Okay, that correlation then becomes the standard for other applications also, other similar applications. Okay, so that means this quantity H cannot be estimated very easily. Okay, so for unlike K, H is not a thermodynamic property of material. It depends on the geometry of the surface, right? Flow characteristics, okay, and thermodynamics properties of fluid. So that's may not be all, but there's some other factors, small factors that influence H value may be there. What do you mean by geometry? Actually, even we can say geometry and characteristics of the surface also, right? The surface may be smooth, maybe rough. Okay, geometry maybe the surface is horizontal or planar wall or vertical or inclined. Okay, so depending on orientation of the surface, the heat transfer rates will be different. See, same hot surface, if it is kept horizontal position and the same fluid is flowing over it, the heat transfer rate will be different. If the same surface, if you keep it vertically and allow the fluid flow over it, then the rate of heat transfer will be different. So that is why, okay, the influence of geometry of the surface is, okay, to be considered in the estimation of H. Flow characteristics. That means flow may be a laminar flow or it may be turbulent flow. Okay. Then the thermodynamic properties of the fluid, the viscosity of the fluid, heat capacity of the fluid, thermal conductivity of the fluid, all these properties also influence the rate of heat transfer. Then we can see there is a very big range for the H values, and these are now nowhere written for a particular case. Okay, it's only a range of the values depending on the flow. So later we will do that. Okay, we have to estimate the Reynolds number of the flow and the Prandtl number. Okay, And based on that, we can select the correlations and all those things. But roughly, you should know that the free convection has less value of H. Okay. The H value is low for the free convection. Free convection in gas is 2 to 25. Free convection in liquid, okay. So, but if it is post convection, then the values are higher. Post convection values are higher. And boiling and condensation, the H values are very, very high. Okay, so this is just to give you the magnitude of this parameter H. Okay, then finally we will take the final mode, that is radiation heat transfer. And radiation is nothing but energy emitted by the matter in the form of electromagnetic waves. Okay, also called photons, and that is these energy emissions are due to electronic configuration of atoms. Okay, change in electronic configuration of atoms. That means when the electrons jump from one energy level to other energy level, okay, they emit the electromagnetic waves, and that is nothing but the radiation. And it propagates with the speed of light, and no medium is required for this one. All substances emit, absorb, or transmit. This is a very big statement. All substances emit, absorb, or transmit radiation to varying degree. Okay, there's a mistake here. Radiation to varying degrees. That means we can classify the materials based on their these capacities: emission capacity, absorption, transmission. Right. So if you have a material that allows the transmission of radiation, then we call that as a transparent material. Whereas if the material is not allowing any radiation to pass through that, then we call it as opaque material. Okay. So then also the radiation is actually volumetric phenomena except for opaque solids. Opaque solids, it is considered as a surface phenomena, and rest of everything, it is a volumetric phenomena. To estimate the rate of heat transfer by radiation, we use Stephan-Boltzmann law, and it says, okay, Q rate of heat radiation emitted from a surface which is at a temperature T is equal to sigma epsilon A e power 4. And the constant here is the Stephan-Boltzmann constant. And then we also have a property of the surface emitting the radiation, that is the emissivity of the surface area, and it is okay proportional to 4th power of temperature. Q is proportional to 4th power of temperature. Okay. So we will discuss in detail the radiation heat transfer and the laws used for the estimation of heat transfer. Okay, all those things in detail in the last chapter, radiation heat transfer. Okay, so this is to introduce you the modes of heat transfer. Since we are taking up these things again in details, so I'll stop it here, and we will continue with the conduction heat transfer in the next class on Thursday. Okay. Yeah, any doubts or anything? If you have any doubts, you can ask now. I'll stop the class otherwise.